Okay, before the break, we were looking at continuous integration, continuous deployment pipelines, introducing them. Like y'all aren't, well, I don't know where you're at. Some of y'all might be ready to graduate, but usually at this class, there's still a couple, when people take this class, there's still a couple of classes left, at least 2 or 3 before graduation. So, depending on when you head out in the workforce, you want to be aware of those modern software development tools, but there's that aspect we've tried to mention a couple times in class that modern software development is not something that fits in a classroom setting. We can look at the syntax of a language and talk about different tools here and there, but modern software development is like 43,000 people working for several years on one application. It's hard to even visualize that in a classroom, but it's still the same concepts that we're learning in the classroom. And when you're on a team, you'll have a small chunk that's like what you do in the classroom, like what you're used to of that really big project. So, yeah, it's not a complete shock, but modern software development is a bit beyond anything that fits in our classroom time constraints. But we can look at the tools and the syntax, and then your part on one of those large teams is the small thing, like what you're used to in the homework assignments. So I guess the biggest change is unlike the homework assignments where you see the finished product run, you won't necessarily see the finished product because your small part you'll send off to the project manager that passes up to their project manager, and you have to wait on the other 40,000 programmers to finish their small parts until you see the program run. It's kind of hard to visualize that in a classroom. But there's also small projects. A good one is to like code new buttons for Word and Excel, Microsoft Office. Just write the script for a macro and then attach it to a new button, put an icon there. That's I found that's often like a weekend's work, sometimes like 2 or 3 weekends, and pays really, really well. And just about every business can do it for those considering freelance things. Might want to look into that one. Open Office suites use Python for their macro scripting. Excel is going to start using Python in the cells. It's out in beta test right now, but the back end is still going to be using VBA. But if you know how to program in Python, picking up another language to make somebody a custom button in Microsoft Word is not hard. And it usually pays really well, and just about every business around is going to use Microsoft Office. You can probably use some customized buttons for those heading in a freelance pathway. So next up is sort of a big one, kind of an important one, but again, anything that fits in our classroom time constraints, it's hard to see how it's important. In the long run, it's one of those things you're going to look back several years from now and be like, oh, that's why he said it was important. And why on Monday we'll be here till 9:30. It's hard to visualize it at this point, but I promise you, in the long run, you're going to look back and be like, oh, that's why I said this was so important. But that's for the future. So let's look up a couple words. Database definition. Everybody knows what a database is, right? We use it all the time. A structured set of data held in a computer, especially one that is accessible in various ways. Relational databases, hierarchical databases, or the file structure, folder structure, directory structure, whatever words you want to use for it. But these folders on our computer fit that definition we just looked at. It's a structured set of data in a computer that can be quickly retrieved. For example, we can go in here and go right back to that Docker one we just did. We can quickly retrieve that data because of the structure. Nobody would ever call that a hierarchical database. If you were in a room full of people that knew that was the technical term for it, they would look at you if you're weird if you use that word, but it fits the definition. Relational databases we usually think of or non-relational databases. So we usually think of SQL. We usually say SQL or non-SQL because SQL is easily pronounceable if we pretend like there's vowels there. Relational, non-relational databases. So relational is like a table. Everybody fills out the same form, so we know the same data points about everybody. We know their first name, their address, their zip code, and every cell on that table would be full. Versus the data we would grab from social media. Right? One person drives a Mustang. Somebody else just had their 25th high school reunion. Somebody else wears size 14 shoes, right? It's just random things. And if we tried to put that into a table, we'd have more empty cells than full cells. But if you're a data analyst, knowing all that stuff is still useful. So we have different methods for those databases. They kind of get categorized all in one, but that's the database. Held in a computer. So the big thing, databases are in storage. Let's have data structure. That's the one we're going to look at. I did not pull the definition up at the top. Geeks for Geeks looks like they have a nice little summary here. I was expecting one of the dictionaries to come up at the top, but they had something else. Organizing and storing data in a computer so that it can be accessed and used efficiently. So our data is long-term storage over on the hard drive. In order to do things in our software, we need to get it into RAM, processed, and then back out of RAM and as quickly as possible, the best way possible. And the best way possible is not an across the board thing. The best way possible depends on the particular set of data we're working with or data. You'll probably notice that I do bounce back and forth between the pronunciations. If I haven't explicitly stated in class, it is a Latin word and we still use it the same way the Romans did. So technically data would be the proper pronunciation, whereas data was just a popular character on Star Trek right around the time that word came into popular usage in America. So, but it's technically a Roman word. Database, add base at the end, that is not a Latin word. That is purely an American word, and that has a long name. It doesn't mean. But data is Latin for which is given. Specialized format for organizing, processing, retrieving, and storing data. Not so much storing. Access and work with the data they need in appropriate ways. That's a nice keyword. I went ahead and clicked on the top results since they didn't give a dictionary for the top results. That inappropriate ways is the thing we want to worry about because we have a collection of data. You're probably immediately thinking of, well, we saw some things. We saw lists and dictionaries. Saw tuples and sets, and we saw a few, but there is kind of a drawback on those. I didn't click on spider, didn't I? There it goes. There's a slight drawback on those, and the list that comes with Python has to be ready to catch everything. Has to be ready for anything people might need for that list, which means there's a lot of overhead. We check the documentation on it. List in Python. The official documentation is way down because they probably assume that only people brand new to Python are going to be looking up lists. So best tutorials first there, but eventually we get down to the actual documentation on data structures, more on lists. So we have all of these methods. And well, look how long that scroll bar is for just talking about it. Over on the right-hand side, we have all of that extra stuff that needs to cover every situation that somebody might quickly come across. But what do you think the likelihood is that we will need every single one of those every single time? Or ever? We're never going to need every single one in the same project. Every time we use a list, we're going to do something different. And that's where data structures come in. We can customize. So let's start there. I'm going to save this. with just our own little custom list. So I'm going to make a new folder on the repository called data structures. Oh, yeah. And here we can see Spider is not on a continuous integration, continuous deployment pipeline because we need to check for updates. So I'm going to ignore and, oh, I was trying to rename that. And all this folder data structures. On the original repository, not the one, the regular class repository, not the one specifically for the CI/CD pipeline. Where should we start at? This is, I'll just call it structures.py. And let's put some class names here and then we'll import them and use them in a different file. Maybe a couple test cases. So I just pointed out a list has a lot of extra overhead in it. So normally this is something we would do in C++ and not in Python, but I'm still going to go through the process of showing what a list is. So let's make a class and call it a list. Just can't think of another name quick enough. What do we need for a list to have? So let me zoom in. You see that better? Yeah. So let's define our init function. Get our cell. And really what a list is just the element of, we have the element and then we need a way to connect all of those things together, right? Let's take element. So really with the list is we're dealing with it one element at a time. So maybe I should have called that element instead of list. And there's a couple different ways to do it. Sometimes we'll make a list and then an inner class or nested class of elements, but I'm just going to call the whole thing list. So there's a self.element, that way we can access it without all our getters and setters. Because that's going to be the element we pass in. And do y'all remember that picture I drew back when we first talked about lists?
Stack heap.
Yes. Oh, not that marker. That's a little better. So in our stack heap diagram, over in our code, we say we'll have a list. I'm just going to say X because that's easy to write on a board. Same reason we use X in a math class. And that points at some data value, the first element. And then an array would have, which we don't have in Python, has an algorithm that finds where the next one's going to start. And we structure it all ahead of time. With a list, we just have a little bit of extra here at the end that points at the next element. Then a little bit extra at the end that points at the next element in the list. And then eventually we get to a point where we have a null pointer, the one that points at nothing. Null pointers are only bad if we didn't expect to hit them. Because if we know a null pointer is there, it takes zero bits to process a null pointer. So when we know we're heading for a null pointer, that's a really, really good thing because we don't even need a single bit to process it. Maybe one bit just to check and make sure it's null and not zeros, but or a different type or void. There are different types, but it takes very, very little bit to process null pointers. They're only a problem when we didn't expect to hit one, when we hit them by surprise. But all we have is the element and a thing to point, something that points at the next element. So that's our other data field. Self. Oops. I have no idea where I was just typing at. My cursor was somewhere that I did not expect it, but
just out of topic question. I forgot to ask that. Why do we mangle the variables?
There's a couple of reasons we might want static variables, but in general, we treat them like they're private. That's the most common usage. We don't have private in Python. Like you had some C stuff before, right? Yeah, so remember the private, protected, and public, we only have public. We only have public and static variables. So since a lot of programmers are used to using private stuff, they use mangled to act like it's mangled. But in general, it also makes a class variable, so it's stored different. If this was a computer science class, we'd spend a lot of time with the stack diagram on that. But software development is just about making it work. But there's some differences. Internally, it's stored as a static variable, so it uses RAM more efficiently.
Static is private.
Static means there's one and only one copy. So if there's only one copy, then we can use the one from the blueprint instead of the one from the instance.
Okay, so if we mangle it, it becomes static.
Semi-static. It's treated more like static in that it will allow us to have we'll have multiple copies if we have a bunch of instances, but it's stored more efficiently. So if this was a computer science class and we were worried about optimizations and efficiencies more than we were worried about working, because software development, we're worried about whether or not the program works. Computer science, we're worried about optimizing and making it as efficient as possible. Then we would spend a lot more time with diagrams and stuff talking about that. But for the most common, that's the design of it. The most common usage is just to a fake private. We act like it's not accessible. This one we want accessible. So we have our element, then we need something that points at the next element. So I'm just going to call it next. Self.next equals null. Or sorry, we're in Python, none. Python has a special way of saying none. But then we can just check, and whenever we get none, which is a null pointer, then we know we've hit the end of our list. That's all we need to make a list. We can start adding things to it. So I have my list, and we'll create it, start with maybe a 3. Oh, whoops, I need to give that something, right? So let's say list, probably not list, not a keyword. X equals that. I'm not feeling very creative this evening. So then we can say x dot next is going to be a new my list. So we have another element with a 4. We could probably do this more efficiently, but now we have our first element has a 3 for the element point, and then the next, the pointer just goes to a new element for our list that's holding a 4. And right now that second one, the 4, has a null pointer because that's what we created it with. I'm gonna do one more layer, and then we'll erase this and do this more efficiently. As soon as some Zoom thumbnails get out of my way, add a bunch of white space so that I can scroll past that next time. So x dot next. So x is the first element. Next is the second. Dot next, and that's going to be another element. So we need to create another element with 5, and I think y'all see where that's going now. That's what a list is. We just have our starting point. We just track where the starting point is, and then we keep pointing at the next one. So that's it'll take forever to initialize that. So we probably want to extend the list with a little bit of functionality. The first one we want is probably an insert method, right? Insert or add. Let's do add, as I see. Obviously, we need self because we're in a class, and I'm going to abbreviate it L. So L. So then we just need to find where the next element is. So somewhere there's a head to the list. We probably want a starting point. This can be moved internally. The element we're adding, actually, I'll put it the other way. The head of the list, that's the standard way. The starting point of the list, our first element, and then L, the next element we want to add. So let's create something called current. And that's going to be the thing we're looking at. Or the head. Probably better to start with the head. That'll be less confusing. There's several ways to do this. Sorry, I probably should have shouldn't be changing my mind along the way. So we have the start of the list and the element we want to add. So we're going to start at the start of the list, and while current dot next is not none, we'll look at the next one. Current equals current dot next. What happens when current dot next is none? That's our null pointer, right? That means we found the end of the list, the spot that we'll put the next element on. So while the next thing in the list is not empty, well, we'll just move to the next thing and keep looking at the next one. But eventually we'll hit that null pointer at the end. And when we do, then we know we're ready for the next element. Current dot next is none. That means next is empty. So then current dot next needs to be that element we passed in, which will actually be it. Probably want to do it this way.
The next is a function to push to the next element.
Yeah, so we just go to the next. So it's just the variable. We're accessing the variables directly here. If you're coming from C++, we can, but for 30 years, teachers have told us that that's a really, really bad idea and not to do that in C++. But so you're used to the methods, but yeah, we're just accessing the variable directly. So the next pointer is empty. Next pointer is empty, and we're just jumping through pointers, and eventually we find which pointer is empty. Sorry, should have said not in that last sentence. The next pointer is not empty. Next pointer is not empty. Next pointer is empty. So we're done with our list. So we'll add the next one on right here. That's kind of all it takes to do that. So then after we create our list, we can add stuff. X dot add 4, X dot add 5, and that probably looks a lot better. X dot add 6, and obviously there's absolutely nothing that stopped us from using the word append, which is the one you're probably used to from Python, right? So I just chose a different word, but that's all the list is. Now we just add the functionality we need. We don't have a way to print this yet, do we? Probably want to see what it is. So let's add a print in there. So define print list, the self, and actually we could just do this in the string, couldn't we? Let's do this in our representation. This is the same as SDR, only added later with some improvements. For anything we see in this class, it is the same as string, but there are better things that can be done with it later. So it's a better version of SDR method. So we need to know what the head of the list is. We do have to know what the starting point is. Oh wait, I forgot that on that adding. That's why I was going to do this. I'm going to take the head out and try to make this as simple as possible. So, because it's always going to be x dot add. So that means we'll set x as the current, and then we'll walk through. What's that? Oh, that's because of this. So we can do the same. That way we don't have to keep passing x in. Otherwise, it would have been like add x and 4, and we need to keep passing that head element in. And we can't just pass the 3 in, right? We need the version that has the next field because that's what we're going to check. So to avoid that redundant looking thing, let's just use the word self in our code and refer to this thing itself. So we'll do that. Current equals self. So we're always going to start at the same reference value. And while current does not equal none, this time we don't even have to look ahead. Eventually, when it equals none, we can just stop printing them. I think I'll make a string to add up. string equals, we'll make it look like the Python list. So we'll start with an angle bracket, then string plus equals current dot element. So the actual element that we're storing in the list. Then we'll go to the next one. Current equals current dot next. And then when we're done, when we've gone through all of them, well, we can add that closing bracket on there. Oh, we probably want a comma here too, right? The current element plus a comma, maybe a space, and cast that as a string. Not typing, going out of left to right, top to bottom order on purpose there. It can be far more productive to bounce around and put the code together in the order you think about it in, not the order it needs to finish in. Because we don't think like computers. But we'll add the current element to the list, put a comma and a space so it's nice and readable. And at the end, we'll close up those curly braces. And it probably wouldn't hurt to do an if statement to, right? If we check the next as none, then we know when to stop putting commas on there. But for keeping it simple in our class example, let's just ignore the final comma. But that's just a selection structure. I feel very confident that all of you, everybody in here could easily put together a selection structure to determine whether or not we need to add a comma each, whether or not we need to add a comma, because we don't need a comma on the last one, but I'm just going to ignore it. Now we should be able to print that. So print X, let's see what happens. Maybe I do need a string instead of a representation. Oh, where did it crash at? So somewhere in the background, line 46, string return non-string. I'm just gonna try this. Let's go back to what I was originally gonna do. Print list. Let's see if that works. X dot print list. This is the one I actually thought about when I was planning for this evening. I didn't crash. Why did it not print?
It's not returning something, it's a function.
Oh, thank you. That's probably what it return string. So that's probably what it didn't like the last time. Let's see if that fixed it all together. Well, oh yeah, it's just returning it. We can see it on the variable list. Oh, I didn't do anything with it. Let me switch that back to the representation because that's probably better form. Return that string that we just built, and now we should be able to print X. There we go. So we built our own list. I feel having graded it, having graded more than one of all of y'all's homework, I feel very confident that you can put a selection structure in here, and everybody in here could probably come up with 3 different ways to avoid putting that last comma in there. Before even getting to just adding \B, before adding the escape sequence for a backspace, like actually doing a selection structure. But right when we get to the end, the escape sequence for a backspace is not difficult. It's a keyboard. It's a key on our keyboard, so obviously we have a way to type it in our code. But I feel everybody could do that. Probably good practice. Lots of different ways to check. But we made our own list. So now we have specifically the functionality we want, and only the functionality we want. There's no overhead coming with this. And then, like Tanae asked earlier, we could make those mangled variables and use getters and setters, and then it's even more efficient on RAM. So if we had something like, say, 10 billion records from a database to process, right? I didn't Google it. I just took a guess based off the cheapest computer laptop at Walmart, but I'm thinking 32 gigabyte RAM is probably average these days. We have bigger than that, right? Or there's a lot bigger than that, but 32 sounds about average, right? Gig of RAM. That's a lot.
Yeah.
16 is probably average.
8.
8?
16 is costly. It goes over $1,000.
Okay.
Around 1,000.
Okay. Well, I was thinking of big scenarios too. So we could easily find more than 8 gig of data. But if we have more than 8 gigabytes in our database, we're probably on company budgets. So then we'll have bigger RAM chips to get up to 32 gig of RAM, and we could still have more than 30 gigabytes of data. That is not difficult in our modern world. In which case, we don't want any extra overhead. We want to minimize things and make it as efficient as possible.
16 gigs, it goes over $900.
That gets expensive quickly. I'm pretty sure I have 8 here on the cheapest from Walmart.
Yeah, it should be around.
And the other things bring it up too. So like an M1 chip, M2 chip's going to bring it up. Brands other than HP are going to bring the cost up a little bit. But yeah, I teach at a community college, so I do make sure I always use the cheapest one from Walmart. Cheapest laptop they have at Walmart.
GPUs bump it up.
Oh yeah, GPU. Well, I have integrated GPU. Task manager.
That really is the cheapest.
Processes.
Yeah.
Oh, it looks like I have 4. 4 gig of RAM, but I do have GPU.
And you read it.
The Intel integrated GPU. I think.
Yeah, once they go
It's only like that thick, so I don't have a real GPU in there.
Yeah.
But yeah. Oh yeah, there's it says it right there, Intel UHD. But still get that. So actually it's probably 4 gig of, it's probably an 8 gig RAM and then 4 gig for the CPU, and then the other 4 gig are dedicated to the integrated GPU. That's the cheap model at Walmart. So that's how we make a list. And then we have these other things, stacks and heaps. Stacks was on that list, major learning objectives, right? So that's really the order that it goes in. So how do we process through this? So we could we could now that we have a list, we could extend this into a stack or a cube.
I had a question. How does it store the, like it's going to the next, but how does it store the values? Like it's not a list yet.
Oh, it does need to be a list element that we put in. So we pass in a number and then it turns into one of our lists.
It's not just one value, it's multiple values. So it needs to be some kind of data structure, what it is.
Oh, that is our data structure. So it's each element just has the pointer. And then when we put them all together, it's a list.
It's getting stored in a heap.
Mm-hmm. Yeah, so the heap is how the RAM chip is organized. We're going to talk about what that is. So yeah, did that answer your question, or do I need to go a little bit deeper?
That's fine.
Yeah, so this is how we most modern operating systems work with the RAM, because this is how the language we're using works with RAM. We can do something different, but in our modern world, if you wanted to do something different with RAM than a heap, you would probably have to make it yourself, because that's
What if I
a really good way. So all of our most common languages are going to set up RAM as a heap.
What if I don't it in a for loop? But it iterate through the
In that case, we would need generator functions. We know how to make a generator function, right? So instead of returns, we need some yields, and then it would feed right into a for loop.
yeah,
I get your question now. Yes. So integrated in Python, yeah. This class is software development with Python, we would probably never actually make our own list, right? It'd have to be a big, very customized project. And frankly, if we're worried about efficiencies and optimizations, rule number one is don't use Python. So we'd switch over to C++,
Yeah.
at least C# or Java, but probably C++ if we were really worried about optimizations and efficiency. That's not the reason we choose Python, but this is software development. And then the with Python is just an add-on. So we have to cover the general software development concepts. Somebody already made this list in Python, but you'll want, it could show up for a need at some point. We just want to cover what they are. We could also start with the list.
Add more functions.
Add more functionality to it. We can extend that, right? We could say, make a class called better list that inherits from list.
Oh, that makes sense.
That makes sense? Then we're not starting from scratch.
Yeah.
But if this is, for the most part, this semester, almost everything in this class is the with Python part. Tonight and Monday are the software development parts. And these are, we're talking about things that should apply to any language, which all have lists in them.
You were just explaining that to explain data structures.
Yes, yes, this is the starting point for data structures. We also have double-headed lists, so I'm going to erase this line, but there's nothing that stops us from putting an and previous pointer here as well, self.previous. So then we can go forward and backward in our list. We don't have to go just one direction. And when we get to binary trees, we have left and right because it's a tree and it's binary tree. So we have two branches coming off of the tree.
These pointers point back.
Yeah, tree structure. So right now we have a list. We have an element pointing at the next element, pointing at the next element, so on. Am I on the camera there? Yeah, okay. So we can put our elements together this way. Usually we say elements per list. We would say node for trees. We could have our root node, and coming off that, we have some branches to the left and right. Here's a binary tree. Maybe one to the right here, and a couple down here, and one over here. And we set it up that way. Instead of pointing this way, we go left or right from our initial root. A stack is one of these, a very special one of these, and a heap is a very special one of these. Those are the two main ones we want to look at.
Previous, it goes from the tail to the head.
Yes, yeah, that would be a good way. So you'd want both, yeah, you'd mark both ends, and then the arrows would point both ways, but fairly straightforward extensions. We only have 8 weeks, and this class is mostly that with Python part. So computer sciences, anybody in the computer science program? You are? Okay, you will take a data structures class.
Yeah, next,
at the 200 level.
Next 8 weeks.
Okay, and are you going to 4-year after that? You will have at least 3 more data structures class. Are you going on to grad school after that? I believe you are. You will have, I'm going to guess at least 10 credit hours, 10 of your 30 credit hours on your master's are going to have to be data structures. Or either that, or you better do a really good thesis on data structures. So it is something you will see over, this is internal working. So this is what usually computer scientists worry about, that optimizations, efficiencies. You get all that worked out, and then you'll write something in Python that the rest of us will just use. Does that make sense?
Yeah.
And then everybody else in the class is just 5 years from now, we'll say import today's data structure.
Yeah, that makes sense.
So that's the difference between software development and computer science. We're both writing code. The focus, though, computer scientists are looking for the optimizations, those efficiencies, making it work as good as possible. So you're more worried about that good as possible part, where software development is works as works. Yeah, we get the client what the client wants as quickly as possible, and then move on to the next project. Most good teams will have a mix of both. They'll have computer engineers, computer scientists, software developers, technicians that are all writing code, but they have a different focus. Technicians would be refactoring. They'd be looking at somebody else's code and being like, oh, okay, this Like this right here, I did not do the white space evenly. They'd clean that up. They'd add comments in and make it look nice. So there's people that their job would just be to clean up somebody else's code.
What is that?
Probably technicians or anybody whenever their workload gets low. There's lots of jobs, but that's one that needs done. And it doesn't have to be your own code to clean it up and make it look nice, right? So it's one of the jobs on there, but there's lots of different layers on the software development teams. And does that help a little understanding the spots? So a stack, let's talk about a stack. That's an important one. Or actually a stack and a queue, because I'm expecting in about 15 minutes we'll be able to extend that to like the minimum version of a stack. And then a queue. It'll be really, really quick. We just need child objects. We just have to talk about them. So a stack is a last in, first out data structure or data structure, whichever one you think fits easier in the sentence. It's English, right? If we mispronounce a word, people will probably figure it out depending on the words around it. Last in, first out data structure. So frankly, a stack of dishes is the best example of that. Right? We finish eating, we wash our dishes, put them up in the cabinet. Come the next meal, the last one that got washed and put away is the first one we grabbed. So we grab the last one, becomes the first one out. That's when we write computer code, that text file, we write top to bottom. The computer reads it bottom to top, which is in a stack. So then that first line we wrote is back on to be the first one popped off the stack. There's terms for that. So that's a big part of this lecture. So even though push and pop are in the list in Python. So great, this is that software development part. We push onto the stack and we pop things off the stack. So unlike a list, right? We fill up our list and then we keep passing all that data around through the whole program. We put things on our stack and then we take them off as we use them. So while we're using it, right? Put 5 things on our stack, like a list, and then we'll turn around and use 3 of them. So we'll take those first 3 off the list. That RAM is now free for something else to happen. Then maybe we add 4 more things back to the list. So we're using that RAM, but 5 lines later, we might use 2 of them. So the RAM, it's very dynamic, and we don't keep it around longer than we need it. When we pop it off the stack, it's gone. We do have .pop in the list in Python. We have .push and .pop, which makes the list of in Python this thing we're making right now. A queue, English spelling, Q-U-E-U-E. The U-E-U-E is silent. I always forget this. Poll is one of them. Poll is remove, right?
I think so.
Like in cricket, the game. Yeah, poll. Poll is remove. What is we poll from the queue, out of the queue, right? Queue is like, well, it's much more commonly used in British English, right? British people, if they're at a office, they're going to stand in a nice little queue in order, and then when the last person getting served, the cashier or bank teller or whoever that queue is for is going to poll the next person in line. So poll out of the queue. And what is the word that goes with poll? I always forget it. I'd have to look it up. Poll and I'll Google it. There's a couple words. We can also use on queue and deck.
Peak.
What?
Peak.
Peek is to look ahead. There's another one that goes with it. Put on a queue. Term for put on a queue. Queue synonym. I always forget this word. There's another set of words that I almost never use them because the pronunciation is even odder than Q. Add to a queue. Why not? Offer, that's it. Thank you. When you get in line, as you can tell, I've never been to London. When you get in line, you offer to the queue. I never can remember that one. Offer into the queue and pull out of the queue, and that's a first in, first out. The line at McDonald's, drive-through at McDonald's, right? First person to pull into the drive-through and place their order is going to be the first person to get their food. I use the washing dishes. A stack is the dishes, and a queue is the food in the fridge because you want to rotate out the food and use the old food first. So the first oldest food is the one that comes out first. We can also say on queue and deck. Those aren't as commonly used. So EN, the prefix for on queue, and deck is spelled DQ. So add the prefix, the common prefix D in front, and somebody decided that word to be pronounced deck. But these are English words, right? Y'all are familiar with the English language. The name Siobhan is a traditional English language. There's no excuse for that. It's like that is not how we use I's and O's or B's or H's. And where did the accent come from? So it's English, and yeah, the name Siobhan is a traditional English name. That is a great example of it. Sorry, little distraction. So on queue and deck are also used, but offer and poll we will see more often as the terms in our built into our programming language. So dot offer and dot poll when we have a queue, which we do have a queue in Python. So you just import queue. You do have to import it, but it's import queue, import queue. It's in the language, and then we have dot offer and dot poll. You can also just remove elements from your list, a list one at a time yourself. That's basically all it is. But let's make a stack real quick. Class my stack needs to extend my list. That way we have that stuff, and we're building our own. Define our init. Whoops. We'll have the self, and instead of using args and klargs, since there's only one parameter, I'm just going to type element to here. Since there's only one parameter, it's actually a lot shorter, obviously a lot shorter to type element here and then pass that up to the parent object instead of putting args and klargs in there. We only have one thing to pass up, and actually that's all we need. We don't need anything else. The thing that makes it a stack is when we take it out of RAM, when we clean it out of memory. So I didn't even have to inherit from that. Well, I'll keep it that way. Super, and it's a parent class, so we have elevated privileges and can access the init method directly and pass the element back up. So that's enough to make it a list or class, and what makes it a stack is how we process it. So instead of the add method, we want a push method. Push. Oh, we didn't remove an element, did we? Let's remove an element real quick. All we have to do is stop pointing at it. Define remove. Self, and let's say element, we'll do L for the thing we want to remove instead of indexes. We'll skip the index one. But again, we'll start at the beginning of the list. Whoops. While current.next, or while current is not the element we're looking for, go current equals current.next. So we'll walk to the next item, look again. Have we done this? Did we do a while else? I don't think we did yet this semester, did we? And Python does allow us to do while else instead of if else. I don't think we've done that yet this semester, but y'all have seen if else, so hopefully, does it make sense what a while else is? That way we have that one for that last pass. So when current does equal to L, we want to jump into the else part. And in this case, we'll say, oh, actually, we need to look further ahead. Because to remove something, we stop pointing at it. So let's first off make sure it's not the first one. If current, so the head of the list, is equal to L, then we want to say current equal to current next. I'm going to put a temp thing in here to explain that. I'll make something called temp, which is the next element. And then I'll say current equals temp. So I'm just swapping those out. Does that make sense? In the classroom, there's confused looks. There's multiple ways to do this. So let's look at the first one instead of looking at it. So if the thing we're looking at is not equal to the element, go on to the next element. And keep doing that until we are looking at the next element. Actually, we have to look ahead here, because otherwise we need a previous. So if the next element is not the thing we want to remove, then go ahead and go to the next element. When the next element is the next thing we want to remove, let's say that if statement will make more sense after this. We'll grab the next. Make sense? Current.next is not the element, and current.next is not none, because if we hit none, we're done anyway, right? So actually, I'm not going to do the while else. While else exists, but it often looks cleaner if we finish our loop and then do another if else. If current, we're always looking ahead. So if the next one is none, we jumped out of our list. So if current.next is none, then we're done. Break out of our function. Otherwise, which actually instead of break, we could just say return. We could do either one. I think every single person put break in their homework. I guess that was in the book. We could also just return and get the same effect there. I'll do that. I will leave it there because I believe every single person did that. Because if current.next is none, that means we got all the way to the end of the list identified. So we don't have anything to remove. But otherwise, we want to set some temp variable equal to current.next. We're grabbing two things out. And then current.next, because remember, current.next is what we figured out the element we're looking for is. So all we do is just jump right over it. We'll just point at the element after it. Does that make sense? Let me put that in a picture on the board. So we have some elements in the list, the head of the list, the second element, the third element, the fourth element, and so on. We start looking. So we start at the head and we look at the next one. Is that the one we want to remove? If it is, we'll do that. But let's look next. If it's not, look next. We get all the way to the end of the list, we'll jump out and just return from the function. But maybe this one is the one we want to remove. So we look at the next. That's not it. Look at the next. That's the one we want to remove. So instead of going to the next, instead of continuing to progress, we're going to stay at this one. And we're going to grab this variable. And we're going to point at that instead. So current.next no longer goes to that one we don't want in the list. Does that make more sense? Picture's worth 1,000 words, that old saying. So if next is the thing we want to remove, then we just put next into the next field. Which will probably bring us to a good stopping point, and then we'll talk about lists and queues on Monday. I was hoping to get stacks and queues. I was hoping to get stack done to save some of the time for Monday, but I didn't really think I was going to. And we're going to be here till 9:30 on Monday, so I don't want to stay much longer. But does the basic idea of a list look familiar there, right? We could start making custom things. So not just removing it, maybe we want to increase certain elements by 3. Right, we'll grab a bunch of stuff from the database and we need to increment the date field by 3 days, or decrement the date field by 3 days to figure out when something happened, or we build whatever method we want, and basically we're just looping through that every time. Adding indexes should seem fairly easy. If you stare at those 2 we have, really the third one in there too, we do the same thing, right? We start at the head. I need another if else on removes. We haven't tested any of these, have we? If L equals current.element return. Oh, wait, not return. Self equals current.next is what we want to do. Probably should set up a temp. This works a little bit better. Current.next self equals temp. That should remove the element from the list. I guess we should do a quick check. Run that. We got our list. Wait till Zoom gets out of our way, and we should be able to do. Right, we have something called X, so we should be able to say X dot remove 5. Oh, we didn't remove it. Why didn't I remove it? I apparently made a next is the element we want to remove. When it is the element, we bounce down here. If none, we're done. Do this. And return. X dot remove. Oh, I know why. Because sorry, I realized what I did. Next is a my list, but we're actually worried about the my list dot element, right? So we need to be doing our comparison to dot next dot element. Current dot next might be none altogether. Current dot next. So that's gonna bring in the full thing, so we got that. Next time, okay. Let's see if that works. All right, X. There we go. So we need to compare the element, not the object itself. Oh, so there's no here. So this is what I forgot. Because remember, next points to another object, not the data point we're holding. But in order to compare it, we need to compare to the data point. Like we said, remove a 5, but 5 is just one of the things that object is holding. That makes sense?
Self is my list.
Self is my list. So in our case, self is X.
In function, current is my list.
Yeah. Yes, because we assigned that to self. So it starts at whatever the first one is. Because it's always going to start at the one we have a name to. Only our first element gets a name. That's another thing about a list. A bunch of people misunderstood that question in the homework, like it asked, did the list change or whatever. A lot of people went through and actually reassigned it, so you actually replaced the value in the list with the upper capitalization. I think almost everybody did that. But the whole point of that, then the point of that question was kind of indicated they wanted you to just print index 2 dot capitalize, and then look at the original list. Was it still the way it was? Was it still uncapitalized in the original? That was the point of the question. So the there's like that that was a lot of people had that misunderstanding. Did I take points off for that? I think I just made a comment about that. Yeah, yes, because it will when you actually replace it, obviously it changes. So there's that discrepancy, and I forgot what I was talking about that led to that. Somewhere it showed up here. Oh, I remember. Only the first element in the list gets a name. So same thing in Python. We have that list and it prints out. It looks just like ours when it prints, right? Square brackets. Doesn't have an extra comma at the end, but that's an easy thing to remove. But really, the name only goes to the first element, and everything else in there is an index. But we could just do while current dot next is not none. Set up a counter, and the first one is 0, the second one is 1, the third one is 2, fourth one is 3, and y'all know it. And just add a counter. So if we want index 5, right? By index, pass in an integer, and while current is not none, start at 0 and keep incrementing until you get to that index. Really easy thing to add, right? I see head nods in the classroom. Hopefully it's a similar thing on that. Maybe play around with lists, add a couple functions. Next Monday, we're going to extend them into stacks and queues. And then we'll make nodes in a tree, and we'll make a binary search tree. And we'll talk about heaps. I'm not going to make a heap, but I will probably point you towards some code if you want to see what the code for a heap looks like. We'll talk about a heap. We'll talk about hash tables. If you're heading into computer science, hash tables are, when we diagram it, it almost looks like a chip, the way we draw it a chip, and it really behaves that way. It's almost at the speed of electricity. But there's trade-offs for getting that. So there's problems with it. The reason we don't just do that every time. So, but that's why hash is in normal language, because when we use a data structure, like instead of a list, we use a hash table, we're retrieving things almost at the speed of electricity. And on something as big as Twitter's database, X's database now, there's a lot to dig through. That's where the hash key came from. Because when we make it a hash table data structure, the diagram looks like a traditional dual inline post chip, the ICs from the 70s. So it retrieves our data from RAM almost at the speed of electricity. Obviously takes a little bit more work, so we have to evaluate whether it's worth it or not. We'll talk about those, that way you'll know what a hashtag is. Finally know what actually know what a hashtag is and why that's common language. We're not going to make one, but I will, at least on a heap, I'll point you towards some code if you want to copy it. We're going to talk about that, and we'll talk about some other data structures. But we'll be turning our list here into a stack and a queue. We'll probably talk about priority queues, and we only have one day for data structures. Computer science students, you'll have to take a whole class on it. Software development students get 1 day in the 200 level class, and if they take the elective where they take 2 languages, they get 2 days of it. So we have to fit a lot into 1 day, and it's like I said when we started this section at 7:20. It's not going to seem reasonable in classroom, but 5 or 6 years from now, when you look back, you'll understand why I said it's so important when we want to really focus on it. So, otherwise, does anybody have any questions about that? That'll be on GitHub in a few minutes. If you want to look at that, maybe make some methods to extend it, try an index, try getting that last comma out of the print function. I believe everybody should, having graded all y'all's code, I have faith that you can do that with no trouble. If you have any trouble, let me know. We'll cover data structures on Monday, and then we'll do some more Django stuff on Wednesday. Otherwise, you have a great weekend, and I will see you Monday.